Welcome back, everybody. We got a fun little calculus question for you. It's an IBSL old exam question, paper 2. So calculators are a green light. There we go. And we're going to need them for a few of these problems. Now, let's zoom in a little bit, get to it. We've got these two functions. F of x is this one here, and g of x is this one here. In fact, let's write even. They give us that g of x is equal to 3x squared. I'll write everything in so we keep everything nice and organized. And they tell us that f of x is equal to 9 over x plus 2. These two graphs intersect at this point, which they call P. And the first question that we're asking is, well, first find the values of P and Q, which are the coordinates for point P. Kind of annoying they use the same letters, but capitals and lowercase, but whatever. IB is annoying in a lot of different ways. Our job is just to do the math. So let's do it. To figure this out, we set them equal to each other. Anytime two functions they intersect, their values must be equal. So 9 over x plus 2 has to be equal to 3x squared. I'm going to set this equal to 0, so rearrange some things by multiplying the x plus 2 over to the other side. So I'll end up with 9 is equal to 3x squared times x plus 2. If I distribute out this 3x squared term over both of those terms in the binomial, that'll help a little bit. 9 is equal to 3x cubed plus 6x squared. So rearranging this, we see that 3x cubed plus 6x squared minus 9 is equal to 0. Now, solving for this, we notice this is a cubic. Cubics are pretty hard to solve by hand, especially with the kind of tools we have in our toolkit as far as the IB is concerned. But remember, it's a paper 2, so what we do, let's plug this into our calculator and let's graph it. Here's the graph of what I just came up with, 3x cubed plus 6x squared minus 9. And we see that really kind of conveniently it intersects the x-axis, so it's equal to 0 when x is equal to 1. So there's our first coordinate. Let's go back. So from our graph, we see that this is going to be true when x is equal to 1. That's our x coordinate. If I go back into any of the two functions and just plug in a 1, I think the easier one is g of x. So g of 1 is going to be equal to 3 times 1 squared. 1 squared is 1. So 3 times 1 is 3. So the coordinates for P are 1, 3. There's the first part of our problem, already worth 3 marks. Second part, B. Write down f of p evaluated, or f of prime evaluated at p. So be careful with this one. We first need to take the derivative of f of x. Then we need to evaluate it at this point, or the coordinate p, which we knew from the previous one is x equals 1. First, let's take f prime of x. To do this, we're going to take the derivative of 9 over x plus 2 prime. I prefer rewriting this instead of writing it as a fraction. I think sometimes students tend to make a few different mistakes especially with the signs in these kind of derivatives. So I prefer rewriting this as 9 times x plus 2 to the negative 1, and we're taking the derivative of this whole thing. Okay, to do this, it's just a nice simple power rule, so we're not going to get carried away. The 9 coefficient stays out there, doesn't change. Then a power rule tells us we can take the exponent, drop it down, so times negative 1. Then we're left with the same thing, x plus 2, that same kind of base, now to the negative 2 power. We drop down the negative 1 and we subtract 1 power from it. Technically, in this case, we would also have to use the chain rule because we have to figure out, is there a derivative on the inside of that x plus 2 that is important, but the derivative of x plus 2 is just 1. So technically we're multiplying this whole thing by 1, but we really don't need to include that. So if we were to rewrite this, I would rewrite this as negative 9 over x plus 2 squared. I'm going to go over here now, and for the last step of this, evaluate the derivative at 1 because we know that p is equal to 1 from part A. So if I just plug in a 1 everywhere, negative 9 over 1 plus 2 squared, squared, there we go, is negative 9 over 3 squared is 9, which gives me negative 1. That's it for part B. Nice and simple. Let's move on to part C. Let L be the normal to the graph of f at point P. So the normal, if we were to graph this, at point P, this would be the tangent of f at point P, which means now I'm going to use yellow maybe. That should be good. This would be the normal. Can't really see the yellow, huh? Let's try this, and you know what? Let's just use blue. This would be the normal, which is what they're calling line L. Find the equation of L, giving your answer to the form y equals ax plus b. Okay. Well, first we need to figure out what the slope is for that line. And to figure out what the slope is, we can actually use what we learned in this earlier part. We already know that the slope of the tangent line is -1, which means that the slope of the normal line is just the negative reciprocal of that. So this we can call the slope m of the tangent, which means the slope of the normal is just going to be that number. The negative reciprocal of that number is -1 over 1. That's how we would calculate the reciprocal. Well, a negative gives me a +1. 1 divided by 1 is just 1. So the slope of the normal line is just going to be equal to 1. Nice and simple. Okay. Next step is then to figure out what the equation for that line is, for the normal line. So it's going to take the form ax plus b, but we know the slope is just equal to 1, so it's going to be x plus b. All we do now is we plug in some points that we already know, and we know this is going to go through the point 1, 3, because that's point P. We learned that already in part A. So let's just plug in these coordinates for x and y and see what b value spits out. 3 is equal to 1 plus b. So we get that b is equal to 2. Therefore, our equation for the normal line is just going to be equal to x plus 2. Nothing crazy there. That's part C, or part C1. Sorry, I should say. Let's actually properly label this. There we go. Part C2, write down the x-intercept of L. Well, this should be pretty freaking obvious. At the x-intercept, it's just going to be at the y-intercept, excuse me. I read one thing, said the other, it's going crazy. The y-intercept is just going to be equal to the value of y when x is equal to 0. So we know that that is just 0, 2. Beautiful. Now, part D gets a little bit trickier, but again, it's not too bad. Let's just work through it step by step. I'm going to erase all these lines because we're going to want to have a nice clean graph for us to work with. We'll see why. Part D, it asks us, let R be the region enclosed by the y-axis, the graph of G, and the line L. So actually I should have probably kept in my line L in this. I'm going to redo the L line was here. This was line L. There we go. So it's asking us that it's telling us that the region R is enclosed by the y-axis, which is here. The graph of G and the line of L. So if we draw all these points, where do those 3 points intersect? They intersect right here. So this is the region R that they're asking us about. And our job now, whenever we see the words, we see areas and regions, usually they ask us, well, figure out the area for me. And the way we do that is integration. So we got to set up a little integral. I'm going to do this down here. That helps us figure out the area of that region R. And to do this, all we're going to do is we remember that integration is always going to take the area underneath the curve. If I take the integral, and we know that our integral in this particular case, we're mostly concerned with area in between those two x coordinates. We know that we're going to be taking some kind of integral from 0 up until p. So I can already off the bat write this as the integral from 0 to 1, because 1 is the x coordinate for that point p, of some curve. Okay, what are we taking the integral of? Well, if I took the integral of just g of x, the integral from 0 to 1 of, what was g of x again? Oh, not g of x, sorry, L. If I took the integral of just L, which we calculated earlier, the equation for L from part C is x plus 2. 2. This would give us the area underneath that line L, which if I do in, let's say, yellow is fine, would be this area here plus everything underneath it. And we don't want that. We want everything, undo, we want everything up until this point where the g of x function lies. So to do this, what I have so far here is actually not fully complete. Let's cross it out. We need to subtract g of x from L, because that would subtract the area underneath g of x, and we're only left with the area in between L and g of x. So the integral from 0 to 1 of L minus g of x dx is like the general form of how we would write this integral. But let's actually plug some stuff in so it makes a bit more sense. We're integrating from 0 to 1 of L x plus 2 minus g of x, which if I scroll up so we remember what it is, because I've already forgotten, is minus 3x squared. And I'm going to put these in little square brackets because we're integrating this whole thing with respect to x. If I integrate this function and evaluate it from 0 to 1, that should give me this area R enclosed by those two graphs as we integrate along the x-axis. So let's simplify this a little bit. I can rewrite this integral as 0 to 1. I can get rid of a bunch of these parentheses. This is just x plus 2 minus 3x squared dx. And to do this integral, all we do is we take the integral of each individual term. So we can integrate x, 2, and 3x squared. Okay, and evaluate the whole thing from 0 to 1. So I'm going to put the whole thing in square brackets. The integral of x is x squared over 2. The integral of 2 is 2x. The integral of x cubed is, or 3x cubed, is in this case just x cubed, 3x squared, sorry. Because if I were to think about this, if I undid this and take the derivative of it, I would bring down the 3 and it would leave me with 3x squared, which is what we started with. So the integral of 3x squared is x cubed. And I evaluate this whole thing from 0 to 1. When you evaluate an integral, you first plug in the top term, the upper bound. You then subtract by plugging in the bottom term. So let's just do that. I'm going to first plug in 1 for every time I see an x. 1 over 2 plus 2 minus 1. And I subtract and when I plug in 0 for everything. So 0 over 2 plus 0 minus 0. What we're going to notice is that all of these terms reduced to 0, so I'm only left with whatever I've got over here. Okay, nice. 2 minus 1 gives me a 1. So a 1 plus a half gives me 3 halves, which is equal to 1.5. And this should be equal to the area R enclosed by the y-axis, g of x, and the line L. Just like that, we've done all 4 parts of this for a total of 13 marks on a really nice, challenging IB Paper 2 style exam question. If you like this content and you want more, subscribe, like, follow, comment, all that jazz, more content coming your way.